Saxon Advanced Mathematics Lesson 22. This is a two-parter, you guys, and we're going to start by talking about absolute value. Remember that absolute value is the idea that if you imagine the number line, for every number on one side, let's call that 3, there is a partner on the other side that has the same numeral but a minus sign to reflect the fact that it's opposite. And if you measure the distance between those points and 0, they will have the same value because they're the same distance from 0. So when we say absolute value, what we really are measuring is the distance from 0. And the absolute value of any number, positive or minus, will always be the positive version of that number. You probably already remember this. Absolute value in the beginning fits in our heads really well. What we're going to practice doing is graphing some absolute values, which we did a lot of at the end of Algebra 2. 22.1, graph absolute value of x minus 2 is less than 0, and want to graph it on a number line. Okay, step 1 is do your algebra to isolate the x, or the absolute value of x. We're not going to take those signs off yet. So for this one, I just add 2 to both sides, and I get the absolute value of x is less than or equal to 2. Okay? Now, the second step is to split into 2 inequalities. And here's the way we do that. We take this one and we're going to split it out into 2 inequalities, and neither one of them is going to have an absolute value sign. We're getting rid of that. And that's the joy of this step. We're going to get rid of the absolute value. I wrote AV in there to remind you. We're getting rid of those absolute value signs. So the first one is going to be just like what we have, only without the absolute value sign. So x is less than 2. The other one is going to be this x with the inequality reversed and a minus sign on there. That little process of flipping the sign and adding a minus creates the second set of conditions that will define this absolute value. Once I write it as a graph, it's easier to figure out. So what we're saying is that the values for x that will make this come true are anything that is less than 2 but greater than minus 2. So I write those two numbers in. I put circles because it's not equal to, it's just the greater thans. And then I connect because that's what they're telling me. So what that means is that I can take any number here and this will be correct. Let's try it just to see. Let's try -1. So the absolute value of -1 minus 2 should be less than 0. The absolute value of -1 is +1. 1 minus 2 less than 0. That's true, isn't it? Because this is -1. All right, so that seems to be working. Let's try +1. The absolute value of +1 minus 2 is less than 0. Okay, that would also be 1 minus 2 is less than 0. That's true as well. Let's try a number outside of our answer and make sure that fails. Let's try -3. The absolute value of -3 minus 2 is less than 0, right? That's what it should be. This, though, becomes, I don't have room to write it, so I'm going to go this way a little bit. 3 minus 2 is less than 0. That's false. 3 minus 2 is +1, and 1 is not less than 0. So once I get my number line graphed, it's easier for me to see the truth in these two statements. When I'm going from here to here, I use a purely mechanical, mathematical process. I don't try to apply logic to this because my brain's not ready to feel the logic in this statement yet. It's only after I draw out the solution that I can test it and prove the validity of this picture. So don't worry about this step. Just let it be a kind of a mechanical process that you know you're supposed to do, and you know later the logic will be apparent. But here, it's not always clear. Next problem. Now, this one's fun because we're going to learn that we actually speak two languages now. And you did this last year, so you know. Example 22.2. Graph the set x is an element of the real numbers such that the absolute value of x minus 5 is less than 2. We're supposed to graph that on the number line. That's exactly like the problem we just did, except it's written in functional notation. So this is the equation we have to deal with. Absolute value of x minus 5 is less than 2. And we've got this isolated by itself. We can't do any algebra to this yet. So let's split this into 2. And remember, we just let this be a mechanical process. We know that x minus 5 less than 2 is one condition. That'll define one end of our range of solutions. And then we take the same expression, we drop the absolute values, but we flip this and we multiply that by minus 1. You might not understand the logic of it, but just trust the process. Now we'll finish up and draw the picture and see if it makes sense. We need to do algebra now, right? Now we've set this minus 5 free. So we'll add 5 to both sides here, and we'll get x is less than 7. And we'll get x is greater than 3. Okay, let's draw a picture and see if that makes sense. All right. X is greater than 3, so that's at this end. No equal signs, right? No equal signs, so that we don't need to solid dot it. 7, and we're still dealing with the reals. You know how we get to the integer sometimes and we have to make dots instead of arrows? Well, we're not there yet. Less than 7. So again, we're looking at a value between these numbers, and let's see if that makes sense. Let's pick the number 4 and see if it works in here. 4 minus 5 is negative 1. Absolute value is positive 1. That works. 1 is less than 2. Okay? Let's try a bigger number, or let's try a little number. Let's try 1. 1 minus 5 is negative 4. Absolute value is positive 4. 4 is less than 2? No. So we just tested it and found that this is a perfectly lovely solution to our original problem, and that this process works. All right. I do these slightly differently than John too. This mechanical process, the way I split it, it's different than what John does. I like my way better. Example 22.3. Graph the set x is an element of the real numbers such that the absolute value of x plus 2 is greater than or equal to 3. Okay, so now we know this tells us we're going to make a dot instead of an open circle. We're still in the real numbers, so it's still lines and not the dotty integer thing. Okay, this time I'm not going to rewrite this out here. I'm just going to go right here. I can see that my absolute value sign is isolated, so it's time to split. X plus 2 is greater than or equal to 3, and x plus 2 is, flip it, less than or equal to minus 3. There we go. There are our two conditions. Now, the reason we didn't have to do anything before is that the absolute value was isolated. Now we clean up our algebra in the second step because this has been set free from the absolute value sign. The first one we did, the number that we worked on the algebra first, that was outside of the absolute value. So we were able to clean that up before we split. If the extra numbers are inside the absolute value, we have to split first. All right, subtract 2. x is greater than or equal to 1 and x is less than or equal to minus 5. Picture. We can draw in the numbers. We need to be at 1 and at minus 5. You do not have to draw anything else on the number line but the parts that you're interested in. So get them in the right order, but you don't have to draw in the little guys in between. And number the ones that you need. Okay, so it's greater than or equal to 1, so I need a solid dot, and I need to go that way. And then less than or equal to minus 5 that way. So this is our solution. If you want to logic check that, you can. Just pick a value in your solution and make sure that it works, and pick a value out of your solution and make sure it doesn't work. That's how you can check it if you don't trust the process. All right. 22.4. Sketch the graph of the function y equals the absolute value of x. Now, if you remember last year, we memorized some of the basic shapes of some nonlinear functions. We memorized quadratic, cubic, absolute value, and square root. If you remembered that, what shape it was, you wouldn't even have to do half the work of this problem. But let's pretend you don't remember. And let's say that we want to graph this from scratch. Okay, so let's just pick some x's and y's. And I'm not even going to add, no, I will. I'll add this middle part. X, y, and our function is absolute value of x. All right, well, let's start with 0 because 0 is fun. The absolute value of 0 is 0. Let's choose -1. The absolute value of -1 is +1. And then let's choose +2. And the absolute value of +2 is also 2. Okay, this makes sense. Oh, I didn't need this here. Ignore those. This makes sense because whatever we put in, we're just going to get the positive value over here. And so we know that all of our y's will always be positive, and we'll just do these points and then extend. So 0, 0, -1, 1, +2, +2. And that's enough to help us remember, oh yeah, remember it went like this. That's the graph of an absolute value function. And we memorized it last year, but it's easy enough to figure out. Okay, reciprocal functions. We're almost done. And this part, if you're with me to this point, yay, celebrate. Do not let this rattle your Jenga tower. John has a habit of going like one step further that I think he should have stopped right there, right? But no, he's got to throw in one more thing and rattle your tower just a little bit more than I think he needs to. But that's okay. We're going to play along because that's okay. Reciprocal functions in and of themselves are not confusing. If y equals x, then the reciprocal function is y equals 1 over x. Okay, that's not so bad. The only hard part of it is the graphing, because John wants us to look at the graphs of these. And I want to show you how they look before... Actually, I don't even want to try to calculate them. I just want to show you this. I don't think he's going to ask you questions about this in the homework. I could be wrong. I'm just glancing right now. Okay. I don't think that he does. So, if we have a linear function, just the one that we had here, y equals x, and y equals 1 over x, we could draw out the tables and pick values for x and pick values for y, and we could graph this out. But I just want to show you what it's going to look like. The graph of y equals x, that's an easy one, right? It's going to be right down the middle, right down the middle. Now, what happens when we graph the reciprocal functions is that they form what we call asymptotes. Asymptotes are lines that curve and curve and curve closer and closer to the line itself, closer and closer to 0, but never quite touch. And this is what the reciprocal function, this is the reciprocal function of this, right? This is x, this is 1 over x. And here's an important tidbit. The graph of a reciprocal function has a vertical asymptote. Whoop. Vertical means up and down. Asymptote means one of these curving lines that approaches but never quite touches 0. It has one at every place where the graph of the original function intersects the y-axis. So that's what John is trying to say here, is that here's where it intersects. So here's where we have them swooping away. Okay? You could forget about that piece of information and you could simply choose values to calculate these two curves. I mostly just want you to see them and see the relationship between them, right? An asymptote in this quadrant and one in that quadrant, because that's where it's intersecting with 0. Or the x-axis, I should say. It is at 0 in this one. And then let me just show you how to do the second. This is the last problem. And we'll just hash it through together. This one we will look at we'll make the table. Sketch the graph of the function y equals 1 over x squared. All right, John, we'll play your game. So let's make a table. X, y, 1 over x squared. Let's start with 1. I like that. 1 equals 1 over 1 squared. That's equal to 1. Beautiful. Easy, right? Let's try minus 1. That would be 1 over minus 1 squared. That becomes positive 1. So look, that equals 1 again. Oh, I like it. So far, this is fun, right? Let's try 0. Uh-oh. 1 over 0 squared equals undefined, blowing up the kingdom. So we can have no value for that. Okay, so that tells us our graph is never going to touch 0. And let's try 0.5, which is equal to 1/2, right? 1 over 0.5 squared equals 1 over 0.25. Which equals 4. All right, we can test that. 1 divided by 0.25. We move the zeros twice there. We move them twice there. Put it up here, 25 into 4, 4 times. Okay, so 1 divided by the 0.25 is 4. So let's look at how that would graph. And you could do a lot more values if you were feeling like that was still confusing you, but let's just look at what we've got. Okay, 1 and 1. -1 and 1. 0 has no value. That means we can't let x ever equal 0. Okay, so we'll come back to that. And then let's look at this one. 0.5 and 4. 1, 2, 3, 4. So what we have, and then let's just try this. 4, 1 over 4 squared equals 1 over 16. Which is 0.25, I believe. Let's just check that. 1 divided by 16. Oh, that's not what I want. Sorry, I don't like the choice of 4. I want 2. So it's 1 over 2 squared. There, that's what I wanted. That number's too big. We don't want to choose numbers that big. 1 over 2 squared equals 1 over 4, which is, there's the 0.25. That's what I wanted. Okay, so then 2 and 0.25 right there. So what happens, and it would help if we did more of these, but this is going to form asymptotes too that are going to go like this. And they're never going to get to 0. But they're going to go like that. That is the graph of the function 1 over x squared. And again, if this weren't enough values, you could keep going, but I don't want to belabor this forever. So that's what reciprocal functions have, this weird relationship to their parent functions, if you will. And let's just remember, just so you might not have this in your head, this is the reciprocal function of this, so let's just draw this in. This would be like this. Whoops, it wobbled. Okay, so that would be what we call the parent function, and this is the reciprocal. So notice that where this crosses the x-axis, where our purple line crosses x, or comes to x, that's where we have the asymptotes that go away in those quadrants, okay? We're gonna dabble with these a little bit. We're not gonna do a ton more with these, so don't worry too much. Let me know if you have questions though, and we'll talk about them. And you don't have to wait till our video chat. You can reach out to me anytime if there's a problem making you crazy. Lesson 22. Yay, good job. Let me look at 23. Oh, we're gonna do more sketching, so. Okay, beautiful. Onward and upward. Thank you, ladies. Goodbye.